So when you have a rational expression that you're trying to evaluate an integral of, if the power is bigger in the numerator than in the denominator, then you might, usually the trick is to break it up by using polynomial long division. So if that's something you haven't done before, there's lots of videos out there. If you just search in YouTube, polynomial long division, you'll see how to do it. Usually the way it works is you write out the denominator, the thing that's doing the divising, and then use that same long division symbol that we used in school. But I'm going to make a little bit of a modification just for organization's sake. Look how I'm putting a plus 0x. We don't have a 0x here, but if you do 0 times x, it makes nothing, and this would simplify back to what we had in the beginning. So this is the same thing as the denominator. And so this is the divisor. This is the thing that's doing the dividing. And then this is what is being divided. And with long division, just like we had long division with plain old numbers, you want to find something. Wait, let me think. Yeah, it's similar to that. It's not the same exact thing. Now we just have variables. You're trying to find something to multiply to x squared to make it be 11x to the third. So we want an 11 and then an x. That way 11 times x squared gives us 11x squared, and the x times x squared gives us x to the third. So if you multiply, you get 11x to the third. And now 11x times 0x makes nothing. And so you can do the same thing that we did with the divisor as with the expression in here. You can put a plus 0x squared, and you'll see why we need that in just a second. Have all your descending powers, 0x to the first power, and then we got x to the 0 power. Okay, so we did 11x times x squared, that makes 11x to the third. 11x times 0x makes 0x. 0x squared, I should say, because x times x makes x squared. And then 11x times 1 makes 11x. Okay, and then just like with long division with regular numbers, we're going to subtract this top part by this bottom part. So if you do that, 11x to the third subtracted by 11x to the third makes nothing. That's gone. 0x squared minus 0x squared makes nothing. And now you got 0x minus 11x. That makes negative 11x. And now if you were to try to find something to multiply to x squared to make it be negative 11x, you're going to have negative 11 over x, like this, right? Because you need to drop the power down by 1. And that's no good. We're actually going to stop here because we're trying to write it without having to use negative exponents. So we use long division. We found out 11x times x squared makes 11x to the third. Everything's working out there. This is like your remainder. And the way you deal with your remainder is, it's just a coincidence too that the remainder is the same as this. The remainder, you add it to what you got from your division, but in the denominator, it's x squared plus 1. It's our divisor. Okay. So when you do polynomial long division, when you get down to the end, and when you can't find anything else to multiply this, and make things cancel out without using like x to the negative first power or anything like that, then that means you've got your remainder, and you write your remainder on top of your divisor. So basically what we've done is we've done polynomial long division. Okay, nothing with calculus yet. We took this and we algebraic, and now that we've done that, now we can start applying some calculus ideas, because we found out earlier in calculus that the integral operator acts kind of like the distributive property. It's a linear operator. It's like it distributes. So you can do this as the integral of 11x with respect to x plus the indefinite integral of negative 11x over x squared plus 1 with respect to x. Okay, so we're kind of through the weird algebra part. This is now just regular calculus stuff. I'll leave this for students to finish. This part should be nice and straightforward. This part, if you don't remember what to do here, you're going to want to let u be x squared plus 1, and that means du needs to be 2x. So I would, here, got to do that integral still. I would rewrite this integral. I'd factor out the negative 11, and then I need a 2 on top, so that means I need to put a 2 on bottom out here to cancel it out, so it perfectly balances out. Okay, so I got you started. That's what you'll want to do with u substitution. Let this be u, and this will be your du, and now you can find your antiderivative. Just don't forget, at the end, you need your arbitrary constant c.